AI regularization techniques deep dive. How senior engineers prevent overfitting and build models that generalize in production. Welcome back to Agentic AI World. I'm your host, and this is your daily AI interview prep. Today we're covering episode 73, AI regularization techniques deep dive. How senior engineers prevent overfitting and build models that generalize in production. If you've been following this series, we've gone deep on transformers, attention, positional encoding, tokenization, activation functions, layer normalization, loss functions, gradient descent, and backpropagation. Today we close the loop on one of the most critical concepts in all of machine learning, regularization. Let's start with the core problem. You train a model. It scores 98% on your training set. Then it hits production and tanks. Sound familiar? That's overfitting. Your model memorized the training data instead of learning patterns that generalize. Regularization is the set of techniques we use to fight this. And in senior-level interviews, you need to know not just what these techniques are, but when to use which one and why. The first and most fundamental intuition: a model that's too complex will overfit. More parameters means more capacity to memorize noise. Regularization adds a bias toward simplicity. It constrains the model to learn patterns that matter, not noise. Let's go through the main techniques. First, L2 regularization, also called weight decay or ridge regression. L2 adds a penalty to the loss function equal to lambda times the sum of squared weights. This shrinks large weights towards zero. In PyTorch, you set this with the weight_decay parameter in your optimizer. The effect: weights stay small, the model stays smooth, and large outlier-driven activations are suppressed. Why does shrinking weights help? Because large weights mean the model is betting heavily on specific features. If those features are noise, you lose. Small weights mean the model is hedging, spreading confidence across many features. That's more robust. Interview tip: L2 is the default regularizer. Always try it first. The hyperparameter lambda controls how aggressive the penalty is. Too high and your model underfit. Too low and it's useless. Second, L1 regularization, also called lasso regression. L1 adds a penalty equal to lambda times the sum of absolute weight values. The key difference from L2: L1 drives weights all the way to zero. That means L1 produces sparse models. Many weights become exactly zero. This is built-in feature selection. When do you use L1 over L2? When you believe many of your input features are irrelevant. L1 will zero them out and give you a leaner, more interpretable model. In practice, many teams use ElasticNet, a combination of L1 and L2, to get both sparsity and smooth shrinkage. Third, Dropout. Dropout is one of the most powerful and widely used regularization techniques in deep learning. During training, you randomly zero out a fraction of neurons, typically 10 to 50%, on each forward pass. During inference, Dropout is disabled and weights are scaled. Why does this work? Two reasons. One, it prevents co-adaptation. Neurons can't rely on specific other neurons to always be present, so each neuron learns more robust, independent features. Two, it's equivalent to training an ensemble of exponentially many subnetworks and averaging them at inference. In transformers, Dropout is applied after attention layers, after feed-forward layers, and to embeddings. Typical rates are 10% in modern large models. Too much Dropout, and you slow convergence dramatically. Interview question: what's the difference between Dropout during training versus inference? At inference, all neurons are active, but you multiply weights by the key probability to maintain expected activation magnitudes. PyTorch handles this automatically with model.eval. Fourth, early stopping. Sometimes the simplest regularization is just knowing when to stop training. As training progresses, training loss decreases monotonically, but validation loss eventually starts rising. That's the overfitting inflection point. Early stopping halts training when validation loss stops, improving for a set number of epochs, called patience. This is model agnostic. It works on everything. And in production, it saves compute. Most teams use early stopping as a baseline and combine it with other techniques. Fifth, batch normalization. Technically, batch norm was designed to address internal covariate shift, but it also acts as a regularizer. By normalizing activations across a batch, it adds noise to the training signal. Each sample's normalization depends on the other samples in its batch. This stochastic noise has a regularizing effect. In transformers, you use layer normalization instead of batch normalization. Layer norm normalizes across the feature dimension for a single sample, making it sequence length agnostic and compatible with variable length inputs. Sixth, Data augmentation. The most powerful regularizer is more data. But if you can't get more real data, you can synthesize it. Data augmentation applies random transformations, cropping, flipping, rotation, color jitter for images, synonym replacement, backtranslation for text, to artificially expand your training set. In modern LLM fine-tuning, augmentation might mean paraphrasing training examples, using teacher models to generate soft labels, or mixing datasets. Mix-up and cut-mix are popular augmentation strategies in Vision that blend two examples and their labels. Seventh, label smoothing. Instead of hard one-hot labels, where the correct class is 1.0 and everything else is 0.0, label smoothing distributes a small probability mass across all classes. A smoothing factor of 0.1 means the correct class gets 0.9 and the remaining probability is spread across all others. This prevents the model from becoming overconfident. Cross-entropy with hard labels can drive logits toward infinity for the correct class. Label smoothing regularizes the output distribution, leading to better calibrated models and improved generalization. Label smoothing is used in nearly every state-of-the-art image classifier and is common in NLP fine-tuning. Eighth, stochastic depth and DropPath. These are transformer-specific techniques. Stochastic depth randomly drops entire residual blocks during training. DropPath drops entire sample-level paths through the network. Both add noise at the block level rather than the neuron level. Used in models like Vision Transformers, DAT, and EfficientNet. The survival probability is typically linearly scaled. Early layers survive more often. Later layers are dropped more frequently. Now let's talk about the interview framing. When a senior interviewer asks you about regularization, they're not just checking if you know what Dropout is. They want to see your system's thinking. Here's the framework I recommend for any regularization question. Step 1. Diagnose. Is it overfitting or underfitting? If your train and val loss are both high, regularization will only hurt. You have an underfitting problem. Add complexity first. Step 2. Identify the bottleneck. Is it data? Use augmentation. Is it model complexity? Use L2 or Dropout. Is it training too long? Add early stopping. Is it overconfident predictions? Use label smoothing. Step 3. Combine strategically. In practice, you combine multiple techniques. A well-regularized transformer fine-tuning run might use weight decay, dropout, label smoothing, and early stopping simultaneously. Step 4. Tune lambda carefully. Regularization hyperparameters, lambda for L1/L2, drop rate for dropout, require validation set tuning. Too aggressive and you underfit. Run a grid search or Bayesian optimization. The bias variance trade-off, which regularization directly governs, is one of the foundational concepts in all of ML. Regularization increases bias, makes the model less flexible to reduce variance, makes it less sensitive to noise in training data. The goal is to find the sweet spot. One more advanced concept you should know for senior interviews: implicit regularization. Modern deep learning models are often over-parameterized. They have more parameters than training examples, yet they generalize well. This puzzled researchers for years. The answer turns out to be implicit regularization from gradient descent itself. SGD with small learning rates and momentum is biased toward flat minima, regions of the loss landscape, where the model is robust to perturbations. This is why model scale plus proper training dynamics can generalize even without explicit regularization. This connects to sharpness-aware minimization, or SAM, a recent optimizer that explicitly penalizes sharp minima. SAM finds solutions that are flat in the loss landscape, which correlates strongly with generalization. It's used in state-of-the-art image models and increasingly in LLM fine-tuning. Let me give you 3 likely interview questions and how to nail them. Question 1. How would you address overfitting in a fine-tuned LLM? Answer. First, I'd start with the basics. Ensure the training set is large enough and the fine-tuning is on a truly representative distribution. Then I'd apply weight decay, typically around 0.01 to 0.1. I'd use a lower dropout rate than pre-training since fine-tuning data is limited. I'd implement early stopping with a held-out validation set. Label smoothing helps with classification heads. For data, I'd explore augmentation with paraphrasing. If the dataset is very small, I'd consider LoRa or adapter-based fine-tuning to limit the number of trainable parameters. That's structural regularization. Question 2. Explain the difference between L1 and L2 regularization and when you choose each. Answer. L2 squares the weights before summing, which penalizes large weights heavily and drives them towards small non-zero values. It works well when you believe all features are relevant but shouldn't dominate. L1 uses absolute values, which creates a sparse solution by zeroing out irrelevant features entirely. Choose L2 for smooth, dense models, the default in most deep learning. Choose L1 when you need feature selection or have high-dimensional sparse inputs. Use ElasticNet when you want both properties. Question 3. What is Dropout and why does it work? Answer. Dropout randomly deactivates a fraction of neurons during each training step. It prevents co-adaptation, forces each neuron to learn useful features independently, and approximates training an ensemble of many subnetworks. At inference, Dropout is disabled and activations are scaled to match the expected value. It works because the noise injection acts as a regularizer. The model can't memorize specific activation patterns. It has to learn robust representations. Let's wrap up with what to remember for your next interview. Overfitting equals memorizing training noise. Regularization equals constraining complexity to force generalization. The big six: L2 weight decay, L1 sparsity, dropout, early stopping, data augmentation, label smoothing. Transformer specific, layer normalization, stochastic depth, DropPath. Advanced, implicit regularization from SGD, sharpness-aware minimization. Always diagnose first. Regularize the right thing. Combine techniques strategically. Tune on a held-out validation set. That's episode 73 of your daily AI interview prep. If this helped you, subscribe and share it with another engineer who's leveling up. Tomorrow we continue the deep dive. See you then.